In this problem, we are told that a projectile has an initial velocity of 105 meters per second and a launch angle of 25 degrees from the horizontal. With level terrain and negligible air friction, how long is the projectile in the air before first striking the ground? Alright, I'm going to draw some level terrain here. Going to draw my projectile on the ground and going to define a coordinate axis at the initial location of the ball. So this will be my y direction. This will be my x direction. And the ball has an initial velocity, v0, and it's being launched at an angle theta. We know that that initial velocity is 105 meters per second, and that the launch angle from the horizontal is 25 degrees. Now, if we take a look, let's draw the path. Particle goes something like this, and then it hits the ground. And then maybe it goes like this, but we're not super interested in that. We want to know when it's here, when it first strikes the ground. So I'll call this point 1 and point 2. Point 1 is the origin, point 2 is the point where it first strikes the ground. Now, if we look at the free body diagram of this particle at an arbitrary position, call this point P. So let's look at the free body diagrams at point P. So we have our ball, and the only force acting on it is the force due to gravity. If we apply Newton's second laws in the x and y direction, sum of the forces in the y direction, the only force in the y direction is Fg, the force due to gravity. That's equal to mass times the acceleration in the y direction. Some of the forces in the x direction are 0. There are no forces acting on this object in the x direction. And that's reasonable, because if there were, it would be air friction. We're told to neglect air friction or drag in this problem. This is also equal to mass times acceleration in the x direction. Now, from these two summations of forces, we can look at the y force minus Fg, which is equal to mass times the gravitational constant, gravitational acceleration, equals MAY. Now, if we cancel the mass, we can see that our acceleration in the y direction is equal to negative g is equal to, well, really, it would be negative 9.81 meters per second squared, since gravity accelerates downward. And our acceleration in the x direction is going to be 0. Now I went ahead and did the free body diagram analysis first, so we can clearly see in this kinematics problem that we have constant accelerations. Now anytime you're doing a kinematics problem, I advise you look at 3 fundamental expressions. The definition of simple acceleration, time derivative of velocity. Velocity is the time derivative of position. And then there's another one I advise you remember. A times the differential displacement is equal to V times the differential velocity. These 3 expressions are a lot easier to remember than the multitude of constant acceleration expressions you can get from the derivation with these equations. You can derive all of those kinematics equations from these 3 equations. So since we're asked about time, I'm inclined to look at these first 2 terms first. We know something about velocity as well. We don't know anything about positions, other than that the starting height is the same as the ending height. But I'm inclined to look at this one first. And now we know something about acceleration too. We know both of our accelerations in our Cartesian coordinate system acting on this object at any time. So, with that intuition, I'm going to give this one a try. And that is the methodology I advise you employ when you're solving problems on your own. Which expression seems to best fit with your given scenario? In this case, it is this expression. So we can rewrite this expression as this isn't exactly fractions. Your calculus teacher might cringe. But we rewrite this as this integral. And since constant acceleration is evident in our problem, we've factored out the acceleration term outside of the integral. And since we're concerned with a change in the vertical height, we know point 1 and point 2 are changes in height. Well, there are changes in x and y, but let's look at the y components first. So if I look at the vector, the initial velocity vector, I can break this down into its component vectors. Vx and Vy, and I'll keep a subscript 0 there. So from trigonometry, we can note that Vy naught is equal to V naught times sine theta. Vx naught is equal to V naught cos theta. All right. Going to erase the free body diagram analysis. Now, if I take a look at this expression in the y component, in the y direction, And I just keep this subscript y here to denote that I'm looking at the y component of this vector. Now our limits of integration, we consider our initial time 0 and our final time t, our initial velocity v naught, our final velocity v, what is our final velocity? Well, when the ball hits the ground, let me relabel the velocity integrals with a y subscript to denote that we're talking about the y velocity. So at the moment the ball hits the ground, at point 2, the velocity in the y direction of the ball equals 0. Even if it bounces, it's going down at point P right before hitting, and then it hits the ground, right? Hits the ground, and then maybe it bounces up, and then it has a little bit more velocity. But at point 2, it has 0 velocity in the y direction. So we know that this is going to be 0. If we solve this integral, I'm going to erase this. It's going to be equal to t ay times t minus 0. I'll rewrite it. Ay times t evaluated from 0 to t equals vy evaluated from v naught y to vy. Now if we perform this operation, we can solve for our time now. So t is going to be equal to vy minus v naught y divided by ay. Vy is 0. We know ay is negative 9.81 meters per second squared. And we have a minus v naught y. V naught y, I labeled it vy naught over here, but it's the same representation. We know that because it's just equal to the initial velocity times the sine of the inclination angle. So let's make some room. I'll scroll down. So we find that time is equal to minus v naught y divided by ay equals negative 105 sine 25 degrees divided by negative 9.81. Sorry about the terrain. And if I plug that into my calculator, you would think living next to the train tracks would result in you never getting any sleep, but you get used to it. And it actually becomes a unique part of living that you enjoy. So our value for time is 4.52 seconds. So that's it for this video. Please like, share, and subscribe. Comment your questions and any other topics that you might be interested in learning about. And thank you for watching. Have a great day.